So in this video, we're going to try to compute two examples. Again, we're working with surface integrals of scalar functions. And so for this integral, I want us to evaluate the function xz over the surface S, where S is the triangular region of this plane. So here's my surface S, kind of a fun little region. And so hopefully you remember from the last section when we pointed out that, hey, if you want to parameterize a surface when you can solve for z, life is pretty good. And here, even though my surface equation wasn't given to me, when I'm given these three vertices, it's not hard to write down this equation. Maybe you should pause the video and make sure you can come up with this yourself. Why don't you do that? Now, once you've got the equation, maybe you don't have it solved for z, but you can see that you can solve for z. And so the point is, if we do that, if we solve for z, then we get z is 1 minus x minus y. And now I know how to parameterize it, and I know what to do for the length of the normal vector. So let's parameterize, and so we get, we get r of x and y. Well, x is just x, y is just y, and z is 1 minus x minus y. And then if you remember, the key formula was that I told you to put this in your back pocket. R partial x cross r partial y is always going to be minus f, let's not put the minus on the inside. It's going to be minus f partial x minus f partial y and 1. And just to be clear, I'm thinking about this as my f. Now, we have to watch our notation a little bit, because the way that we're writing these, we might think of this function as my f. And so a lot of times when I do these from now on, I'm going to use g for the surface. So I would write minus g partial x minus g partial y and 1. And I'm going to think about that. Let's put it in red here. This is my g of xy. So that's something you want to have in your back pocket, just because it speeds it up. It's not a big deal. Please, I hope you're very comfortable computing r partial x here, r partial y here, and then just take their cross product and you'll get here. But if you know that, then you can save yourself several minutes of time, and it will actually make you feel better about lots of things. So the point is, when I compute this, I just get, well, minus g partial x. Let's look at it. So right here, g partial x is going to be, g partial x is minus 1, and then minus that is 1, so I get a 1, 1, 1. All right, and so the point even more is the length of rx cross ry is just square root of 1 plus 1 plus 1 is square root of 3. And so now I'm ready to set up my integral, so let's go up and copy it, just so that we don't have to rewrite it. And so this integral becomes the integral over the region D. Now the region D, let's be clear, the region D is going to be the region in the xy plane. We'll get to that in a minute, but let's just shade it here so that we can see it. This is in the xy plane. That's my region D. So this is going to become a double integral over D. Again, D is just the region that your variables are allowed to operate in. And I'm going to replace x with just x, and z I'm going to replace with 1 minus x minus y. And then I'm not going to decide how to cut this yet, so I'm just going to say dA. Oh, I forgot, it's not dA. It's times the length. It's times this guy. It's times the length of r partial x, r partial y. And so I get a root 3 dA. And now I'm going to sketch my picture of the region that I'm integrating over, and it's not too hard to see that this line, when z is 0, then this is just x plus y equals 1. And so that looks like this. That's the region that I'm integrating over. This is x plus y equals 1. That's the line up here. And so I'll cut this vertically first. I'm going to cut this as a type 1. I'm going to get the integral. Y goes from 0 up to 1 minus x. Please check x goes from 0 to 1. All of this you can check yourself. Let's pull the root 3 out. And we'll put a root 3 out here, and then I just have, let's push the x through, and so I get x minus x squared minus xy dy dx. This one is one you can work out. I would say this: if you are confident looking at this, that, oh yeah, I can do that, then don't stop it and work it out. If you're a little unsure, which means you're not going to want to stop it and work it out, then you probably should. And just make sure that we're comfortable. This is just double integrals back from chapter 12. Really shouldn't be a big deal at this point. So that is the value of the double integral. And so the key takeaway is, again, don't forget that when the surface is given by z equals g of x, y, the length of your rx cross ry is, I'm going to slip a negative in here. It's fine. The square kills the negative, but I guess I want you not to forget the negative. So it's minus g partial x squared plus minus g partial y squared plus 1. I hesitate to make this video too long, but I think let's go ahead and do one more example just so that we don't have too many videos. So this time we're going to work out a problem where our surface is not, I can't define it as z equals some function of x and y. Here I'm given a parameterization. And so I'm going to have to work it out directly. That's no problem. I know what to do. So I need to compute r partial u, and I'm going to get what? Cosine v, sine v, and 0. And then I'm going to compute r partial v, and I'm going to get minus u sine v, u cosine v, and 1. I want to compute their cross product, and I'm going to get r partial u cross r partial v is what? Sine v minus cosine v, and then I'm going to get a u cosine squared v plus a u sine squared v. Oh, that's nice. So I can pop the u out, and cosine squared v plus sine squared v is just 1. So the point is that when I simplify this thing, let's go ahead and write ru cross rv is just going to be what? Sine v minus cosine v comma u. I'm interested in the length. Don't forget that you want the length. And so let's say, so the length of ru cross rv is going to be what? Radical sine squared v. The negative is gone. When I take minus cosine v squared, I get a cosine squared v plus a u squared. So this is exactly just 1 plus u squared. So that's nice. Okay, now I want to look at my function f that I'm integrating. All right. And so I want to think about f of r of u and v. Well, f was radical 1 plus x squared plus y squared. X is u cosine v, y is u sine v. So I think we can have this all on the same screen. I'm going to get radical 1 plus u squared cosine squared v plus u squared sine squared v. Again, factor the u squared and you get a cosine squared v plus a sine squared v, which is just 1. So this becomes the radical, excuse me, of 1 plus u squared. Interesting. These are actually the same. We didn't make a mistake. These are the same. Let's just keep going. Let's set up our integral. Maybe we'll copy the original integral just to keep things very clear. A lot of you guys don't like to rewrite that original integral, but it really is nice to be able to read your notes if you write each step down. So the original integral that I want is going to be the double integral, and here I am going to go ahead and do my bounds right away because my bounds are just constants. This is working over a rectangle in the UV world. So let's just integrate this du dv. So u goes from 0 to 1, v goes from 0 to pi. I get f of r of u and v, which is this radical 1 plus u squared, times the length of ru cross rv, which is also 1 plus u squared radical, and then I get a du dv. I do want to make very clear to you what's what here, so please realize this is my f of r of u and v, and let's find a different crazy color. How about this one? Oops, oh man, I can't write today. This is my r partial u cross r partial v length. And so it just so happens they're the same. Well, that makes computation easy. Otherwise, we have this nasty radical to deal with, but they kill each other. maybe we should find a better way to say that. They blend together into a nice clean polynomial 1 plus u squared du dv. And so I won't work this out. You're welcome to pause the video. If you have any doubts about your ability to do that, then please go ahead and pause it and check that you get 4 pi thirds. All right, so we knocked out 2 examples, so let's go ahead and break this video here, and in the next video, we're going to move towards our next goal.